Okay, so what we will do today is to finalize our part of array antennas. So we will look at 2D arrays and a little bit of millimeter waves, and first some part of a different way to steer the arrays. There are phase steering or like beamforming, how you can do it. There comes a few different approaches. And then in the end, I will also go over to this, the bit of this method of moments. So the things that sits inside of the simulation software that you've been using to design your patch antenna. Okay, so let's get going with the first part here. So in these cases of arrays, we have in this course, or we are in this course, focusing on really the array and the array elements. So what we've been learning, or what you've been learning here, is really how do we do with these arrays from the perspective, in some ways, of what's sitting and outside here. So we have the antenna elements, and these antenna elements is what sends out the radiation. So here we have these EM waves. So we've been looking at how we go from either some coefficients, typically some AN, or some JN that sits on these elements, and then we can determine the field. And we've been looking at approaches then to say that we would like to have a specific pattern. How should we choose these coefficients, excitation coefficients to this array, so we get the wave to propagate in a certain direction, or having a certain shape. So for example, low side lobe levels and so on. Of course, to do this, we need electronics behind the array. And there are many ways of doing that kind of electronics, and we will not go into that in this course, but there is two main parts that I think is very important or essential to actually know in these cases. So the first one here is this analog beamforming, and that is the traditional way of doing an array. It's usually called a phased array. So what you have in that one is that you have some processing that sits down here. If you think in a communication system, it means that you do the baseband signals that contains really the information you want to transmit in some ways. And then you have some amplification, and you can change this one. You can change it in frequency. You can modulate the signals to the frequency you would like to transmit. And that comes a little bit later in some ways, somewhere here. And then in a phased array, there is one more step. And there are some phase shifters here. So this is another electronic component that changes the phase of the signal. And as you noticed, if you would like to propagate in this direction, like in the broad side in this picture I have, then all elements here should have the same phase. If all the currents on these elements, like J1, J2, all of them have the same phase, you add up constructively in the broad side direction. If you would like to radiate in another direction, for example, upwards here, then you should change the phase of the elements. And it might be easier to think about it, and actually in some the hardware of this, you actually do what's called time delay lines in these ones. So you can either change the phase, or you can actually do a time delay. And a time delay is that you change the phase. So of course, if you would like to propagate here in a direction upwards, what you should do is that you should start sending the signal there. They should start early, and the element up here should come late, because that element is a little bit closer. So by delaying these elements here and these components here, you can then steer the direction of your beam. And that is what's called a phased array, or analog beamforming in this case. So that is, in some ways, the most traditional way of doing this. And it is the one that requires the least amount of electronics. It has, of course, one shortcoming, and that is that it's only one baseband processing in this case. Of course, I could make two, I could make three there, but it's essentially like one or a few of these that you send at a time. And if you think about a MIMO system or a modern communication system, there you would like to have many of these basebands. You would like to send many signals at once. And then you need many of these RF chains. You basically would like to put one RF chain to each element. Then you have individual amplitude and phase control of every element. And that is usually called instead a digital beamforming. So here we change the process of this, of saying that we have many parallel streams of these signals. So I can have some baseband signal here, I have another one here, I send it to its own RF chain, which basically means amplification, modulation, so you can increase the frequency to the frequency you would like to transmit, and then you send that signal out to its element. And that means that this one sends some signal, the next element here can send whatever signal it would like. Each of these, of course, very broad. So if you think about the dipole, each of those would transmit something like this donut shape. And then you add up with all other ones there to get the pattern you would like to have. And this is then digital beamforming. So it in some ways requires more electronics to each element. And of course, if we have these versions with an analog and digital, and we can see that one gives more freedom, you would have a better communication system, but you would also pay a higher price because you have more electronics. Of course, there's a hybrid of this. So you can do versions where you combine in some ways a few of these phase shifters, time delay lines, and a few of these in some ways. So you can do combinations, or I should have even included this one here. You can include more RF chains, and then you can have a few phase shifters. You can combine this in different ways. And this, of course, comes to what to say, a cost performance ratio. So you need to keep the cost down, but of course you need to have the performance up. So maybe you go somewhere between all of these ones. And that is in some ways what sits behind this. And when we in this course have been talking a lot about these signals, what we say is that what's transmitted here is just one of these excitation coefficients. So it's something that has a specific amplitude, it have a specific phase. And then we have different ways to generate that with the electronics that sits behind in this array. And there's of course a lot of signal processing going on in some ways. So that is one view what sits behind all of these arrays. And then one thing that is happening right now with all of these arrays is that arrays is going from something that used to be a radar technology, I would say really a military type technology. It existed in a lot of military applications, not that many in civilian applications. But that is changing now. Now these arrays are coming in a broad sense to mass markets in some ways. And to do that, it comes in the same way as we go to these millimeter waves. So you know when we now go to 5G systems, so what is coming or already is in the market for some areas at least, there we have millimeter waves in our cellular phones. So in these devices, that's it's millimeter waves, not in mine, but in others. And when you do that, you suddenly also start to get arrays. So this comes together in some ways. And in the same way as it comes in radar technology, for example, it comes in cars, it comes a lot of cases where we actually start to see arrays in a civilian market in some ways. And for almost all cases, it is connected to these millimeter waves. So of course we can think about why didn't we have these big arrays, for example, for 1 gigahertz and so on. Of course, I should also say in this case, like MIMO is a certain type of array. So in that case, it actually exists in the lower frequencies too, but then very small arrays in some ways. So if we think what's happening when we would like to have an array, one essential thing that we've seen in almost all our cases, so the arrays that we've been looking at, it's been dominated by this antenna spacing, which is around half a wavelength. It can sometimes be slightly more, it can sometimes be slightly less, but it is of the order half a wavelength. So maybe sometimes it goes to lambda over 3, and maybe to sometimes almost up to 1 lambda, but it is in that order of a wavelength, so half a wavelength. If we think what that means, if you sit in a system of 1 gigahertz, You know your wavelengths, that is your favorite wavelengths, 1 gigahertz, it is 30 centimeters. So 0.3 meters, that is 1 gigahertz. And that would mean that, of course, you have an element spacing of half a wavelength, which is 15 centimeters. And that's quite big. And if you now think you would like to have an array, so let's take a decent array here. Let's say that you have 8 elements in an array. It means that your size is 1 meter. So in some ways, it just comes from this. You have 1 gigahertz, you need a few elements to get an array. In this case, I took 8. And that means that your device has to be 1 meter. And then if you think about a civilian application, like a personal electronics application that you have, why would you like to carry something around that is 1 meter? It's too big. You cannot really do it. 1 meter is too much. So we need to, in some ways, shrink the sizes of this to make it into something that we can actually use, because we can carry it around. It fits in our pockets in some ways. We don't want to carry something that is 1 meter in size. So 1 gigahertz is in some ways a frequency that is too low. The wavelength is too long to really create an array. Then, of course, in these phones, like 4G phones, there is an array because there sits 2 antennas, for example, around 1 gigahertz. And in these cases, yes, you can put 2, because you can always have, for example, dual polarized ones. And even with the spacing you have here, if you're putting on the edges, two dipole antennas are kind of okay. They are not totally correlated, so you can actually use them in a MIMO setting. But it's not an array where you think beam forming, sending a nice beam, that you need larger sizes. So if we start going up in this frequency, we go to 2 gigahertz. That's, of course, pushing it down to 7 centimeters. So we get half of 1 gigahertz. You don't have to calculate the spacing one more time. And if you would like to have 8 elements, of course, then will be like half a meter. So in handheld devices, of course, you cannot do that. It's still, I mean, it doesn't really work. But in base stations, perfect. So in base station, you can start building these arrays, because the base station you don't have to carry around. It's fine to have a quite large base station, but your devices here, of course, have to be small. You could take like a laptop or something. Of course, in a laptop, you can start fitting these kind of things. There is enough spacing in a laptop to put more antennas. So it comes to these sizes where you sit in this. And if you go to the 5G frequencies that are coming higher and higher now, the wireless LAN and so on, if you go to 5-6 gigahertz, then you're down here to wavelengths of the order of 5 to 6 centimeters, and you have a spacing of 3 centimeters. Yeah, here you can start fitting stuff. In these ones, it could fit, but of course they're still quite big, but you can put more antenna elements in there. In these kind of stuff, yes, it fits. Absolutely, you can start getting into these kind of devices. But to make it really practical, you would like them to be even smaller. And when you go to these smaller ones, you can go, for example, to this 24 to 28 gigahertz bands, so around 30 gigahertz. If you do 30 gigahertz, it's of course 10 centimeter wavelengths, so rather short wavelengths. And these are the millimeter waves, because now the wavelength is of the order of millimeters. So usually the ones that goes to 10 and shorter are called millimeter waves, because you measure them in millimeters. And then you would have an antenna spacing here of around 5 millimeter. And then if you have these kind of devices, of course, you can still fit them in a rather small space. 8 elements fits in 3 to 4 centimeters. Go down to 4 elements, of course, then you can fit them like in 2 centimeters. And then they mean this device is suddenly big. So you can really fit these arrays into these devices, which of course give them the power. It also gives a cost, because to do the electronics of them is power hungry, which is a problem for these devices. The next advantage we really get, and that is the big advantage, that is when you go up here in frequency. So of course, when we go up in frequency in these cases, you get an enormous bandwidth. And that is why you push up to these higher frequencies. But when you go there, you get an advantage which is additional to that. That is, you can shrink the size of your antennas. So they get small, physically small, not electrically small. So they're only small compared to like how many meters are they, not compared to how many wavelengths they are. They can still be half a wavelength in size. So perfect antenna size when you go there. And you get an enormous bandwidth, and that is good for communication. Of course, the free space path loss is longer because you need to propagate more wavelengths because the wavelength is short again. And that means that you can compensate that with an array where you can get a narrow. So it goes hand in hand what you want to do with these kind of systems. If you then want more ports into your system or array one for communication, of course you can use dual polarized elements. So if I said now 8 elements, yeah, they could be single polarized 8 elements. It means you would actually have 16 channels because you have 2 times that if you do them dual polarized. And if you do instead 4 elements, yeah, you could have 8 ports. So you can transmit on both polarization at the same time, but you don't get an array gain in the way that the gain or directivity is increasing. Then what's happening in beyond 5G? You know, nowadays we are sitting in the situation that you can buy these 5G devices. There's still enormous amount of development in the 5G technology, but of course the research is pushing now away from 5G, and people are start speculating already about 6G. I have no idea what 6G will be, but there is a lot of ideas what will happening when we go past 5G in some ways. And one thing it seems to be quite a lot of consensus about is that there will come higher frequencies. So there will be an increase here of a first step going to this around 30 gigahertz, and then there will be higher and higher frequencies because of course the available bandwidth can be enormous up there. There is free spectrum up there, a spectrum you can use, and you can get huge amount of bandwidth up there. So there is a trend to move up. And that means again that the antenna elements shrinks, so you can fit more elements into a small footprint in some ways. That goes hand in hand in these cases. So if we think what this can look like, if you take your cellular phone. So this is a very early prototype for 28 gigahertz. They are on the market nowadays, not these ones, but this is an early test. So here you can see quite a lot of antenna elements. And this, of course, just ideas, what elements can be good, what can you try? And a thing what's happening now when we go to these frequencies is that we don't need miniaturized antenna elements. So we don't need things which are called electrically small. If you remember, you took your dipole and you did like this. You did this meander line. It shrinks the footprint of your dipole. You don't really need to do that when you go to these frequencies. Here you can have elements which have their natural size in some ways. So this is not really needed when you go up here. Here you can fit full-size elements. You cannot do that at 1 gigahertz because you will need 15 centimeters, which is typically the size of your phone. And in this case, here is some elements you can just see in there in the center. You can see some patches and so on. You can see different types of antenna elements. You can have connectors, and you can try to see and understand what's happening in these cases. And the big thing is that you really fit these cases. You fit elements which are around half a wavelength, slightly, of course, slightly shorter. It's totally fine, lambda over 4 or something. And you have a spacing which is around lambda over 2. It fits very, very well into these kind of devices. And nowadays, of course, these are on the market. You know, they are already released in many countries and so on. And this is, for example, one example here. This is a Samsung version. And when you have these arrays, of course, you need to put the arrays somewhere. And it starts to be, you know, a problem because these devices are full with everything. And then it comes a user of them. And of course, if you put your fingers above some of these ones, they don't work that well. This radiation really can be stopped in some ways by your hand and so on. It doesn't really go through in that cases. So one option is, of course, that you put it on many different places. So then hopefully at least some of these will work. And also you don't have an array with complete control of the radiation pattern. If you have an array here with 4 elements, they can be dual polarized elements, you have some scanning capabilities, but it's anyway quite limited what you can do with it. So it's good to use different, what to say, edges of it. You don't put all of them like on the top here. You can have something here, it radiates mainly in this direction here. You can cover some plane here, and here you can cover some plane there. And you try to get coverage because you don't want your user to take your phone and say, okay, I have my base station there, I have to tilt it like this to work. That, of course, the electronics in your system should adapt to. It should find the way to use this module in these cases, use the beam steering to find actually the direction it should pick the best ones. So you need to distribute it in different places. And nowadays you can buy basically chipsets which contain all the electronics, it contains all the antenna elements that sits there, and you can then integrate this into your devices. And the footprint of this are, I would say, small. You can see here, this is some illustration here. Of course, from a manufacturer perspective, they are still typically too big because they will take space somewhere. They don't go through typically the screen of your phone, so you have to put them somewhere along the edges, or you can maybe have them on the back somewhere, but typically on the edges. And it starts to be very, very squeezed with space because you have all other old frequency bands that sits there, and everything has to coexist into these devices. But it's really one case where you see arrays. Arrays are really coming, and when we see the future, one thing is for sure, there will be more arrays in these kind of things. Arrays is coming almost everywhere here because it gives a processing gain where we can do a lot of things, which means arrays are good in that sense. So, of course, in these cases, we can go up higher and higher in frequency. So this was 30 gigahertz or 28 gigahertz, the previous one. 60 gigahertz is a very popular frequency band. And this example of a 60 gigahertz antenna. In these cases, there is not, any control at all. You cannot do beamforming. What you can see here is microstrip lines that feed it. So you could have your coaxial cable somewhere here, and then it goes in here and it distributes out to the elements. We will look a little bit closer to that very, very soon. So when we go to 60 gigahertz, yeah, you have a wavelength of, in this case, 5 millimeters. So you're 30 centimeters divided by 60, half a centimeter, so 5 millimeters. And in this case, if we just do the calculation, you know the approximate size of your patch antennas. These are patch antennas. In this case, they would be approximately 1.7 millimeters. Pretty small. Imagine this week, you're going to build your patch antenna. Luckily, it's not the only millimeters because it's pretty hard with a pair of scissors to do these things. They start to be too small for humans in some ways. You would like to have something that is, instead of this kind of size, something you can hold here, which is typically down to like, 2 gigahertz. It's a good size for what we can build ourselves, which is what you will do in the lab. You had a thickness of your patch, I think, of some millimeters. You can see in this case here, you have a dielectric substrate, it's a Teflon substrate in this case, of like 0.1 millimeters. So incredibly thin. These things start to go down to the sizes when we go higher in frequency because we want them to be thin, like a piece of paper or something. Incredibly thin structures. And if we look at one array here we can see what I mentioned before, that there is a feed line. So the signal here is coming like this. And what you would like to do in this array is that you would like to increase the gain or the directivity of it. So you want to make the beam width more narrow, which means that you would like to have the same phase of all elements. If all of them have the same phase, they radiate in the broadside direction out from your screen, because that is the same, phase level on all of them. There is no then direction on it. It goes straight up. It's the same direction to all elements if you're straight up. Which means that what you need to do is to create a path here. You can go to one element here. So if I go to this one, the phase has to do with how long path does this signal have to propagate. That is the dominant factor. And if you see here, this is the same to all of them, because if I take these ones instead, you can see it just divides in the same way. So you draw this line here that the length is the same. And then you have to impedance match it, so you don't get reflections, and you fix the impedance by fixing with the width of it in some ways. That is the dominant factor for that one. So you divide it here from a thick line to thinner lines because it divides into two. You have to change the width of them. And then the next thing you have to do with these ones is also to match them. And the matching is done, you can see, for example, up here, that suddenly it gets a little bit wider. That arrange for the matching of them, so you reduce the waves that are propagating forward and back. You reduce the reflections there. And then you can see that these are microstrip fed patch antennas. So of course the dominant radiation comes from these currents that sits on these sides. And these things that goes in here is approximately the same as your feed point when you have your patch antenna. Like you have this SMA connector on the one that you will build. And when you do it on this printed technology on a substrate, you instead make this little bit edges that goes in here, and then you push in your feed point, and that adapt for the radiation resistance, so you can get it into the impedance of your transmission line. It doesn't have to be 50 ohm in these cases. The ones that sits for these patches can be any other number. It just should fit to the line that is coming here, so you don't get reflections. But otherwise, the design rules for these rectangular patch is the same as you have learned and you are doing when you design your own rectangular patch. But then, of course, you have to do the feed network, you have to do a lot of things around it, but the basics is there. It's the same thing that you've been doing. So that is a typical, in some ways, array. And as I mentioned here, this dimension then is the length, and that is in this case approximately 1.5, 1.7 millimeters. So very, very tiny devices. Another one with the same is that, of course, you can buy these with complete modules. That the one in the phone, they can all even do beam steering. This is a few years old here. And this is a similar thing here. And here is like a module which has, what to say, everything needed to it is just connect your, in some ways, cables into it. And this is a stacked version of patches. And they have what's called dual it has parasitic elements above it. So the elements that you can see here, they're also patches, but there is a patch below that that is really the driven element. And then putting out an array, so it's 4 times 4 in these cases. So the same as here, these are also 4 elements. And in this case, it's also 4 elements. But then these 4 elements are divided into sub patches. So actually you can see there it's 16 in these cases. But below the layer, you don't see there is 4 times these ones. And that's increased the bandwidth for this kind of array. So again, very, very tiny elements that sits there. And now we do one change of these arrays. So before in the course, we had looked at this 1D arrays, so typically one of these. That is what we really have studied. That is what we studied when we look at the beam steering. That is what we studied when we do the element patterns or the array patterns and so on. Now, of course, you can also go in this direction. So this is really 2D. There are elements both in X and Y plane in these cases, which means we need to study what happens when we put array elements in 2 dimensions instead of 1 dimension. That is a 2D array in these cases. So that's what we will do now. So we go from our 1D array to 2D arrays, and we do exactly the same thing. We don't change anything, it just gets slightly more complicated. So if we think about our 1D array, that is that we have elements, for example, along the Z-axis, or as here along the X-axis. When we do a 2D array that sits in below here instead, of course, I have elements that both depends on the position in the X direction and position in the Y direction. So I have to say again, where are my antenna elements? And they are in this case equivalently spaced, so the same distance between all of them, dx in the X direction and dy in the Y direction. And then I just have some index to calculate where all of these array elements are. And if we do that, we do the same thing as before. We just calculate our array factor, and the array factor said that we should use this phase factor. It's the same when we do the radiation vector. It was the same in the 1D array. Of course, it's the same in the 2D array. It only have to do with the distance from your antenna elements to the observation point. And then you take away the average distance in some ways. So the perturbation from that one. You weight that with your coefficient and you sum everything up. And if I have my array in the beginning in the x and y direction, I can put in here what my r hat is, and then I can compute this with a slightly more complicated formula that could contain then sine theta and cosine phi and so on, sine phi. And I can sum up all of them. And now we can see it was slightly complicated in a 1D case. Now it's of course much more complicated because we have two versions or 2D on these ones. So what we will do is we will actually simplify this into a specific case, which is the one we will use in this course. And that is that we assume that our 2D array is the product of two 1D arrays. So let's make an assumption here that these coefficients to this 2D array can be written as a product between the 1D elements here and the 1D elements there. So I divide it into these cases. It simplifies the analysis a lot, and it pushes us back to 1D arrays. So if I do that, I have the same thing as before. So this is what we had written up in the previous case. But now, of course, this part here depends on y, and this part depends on y. So I can sum those one there, and I can see that this one here depends on x, this one on x, so they go there. And then I can separate, in these cases, the summations here. So now I have two 1D arrays, and the result is that I can take the product between them. So when my excitation coefficient here separates like this, then I can also separate my array factor in the same way. And since we are now experts on one-dimensional array factors, of course, we are directly experts of two-dimensional array factors in this specific case, which is the one that we will do in this course. We will not push it further because it doesn't give that much, and it's mainly technical in some ways. So we have the product of two 1D arrays. So let's look at the uniform planar array. We derived it, let's see, I think it was on last week. A week ago, we did a uniform array. And there we can show that the 1D arrays, they look like this. So that was the array factor for the 1D array. It's not the sinc function really. This is the discrete version of it when it comes to the Fourier transform of these cases. When we do the 2D array, yeah, then I take this one here and I have to multiply it with the next component there. And then I just do all the x into y. And then I have the total pattern as it's there. So the product between these two patterns. And that means if you think about the 1D array, you could control it like this. So you had a nice beam in one direction. Now you will get it in two directions instead. So you really get a beam going out. But you need this 2D array to get it to really propagate like a nice narrow beam. And this is then what it can typically look like if we do beam steering. So beam steering is the same in a 2D case as in a 1D case. We had these phase factors that we had to use. And again, they just separate into the product of two. So this 2D array can be seen as the product between two 1D arrays that are steered. And now you can think about the pattern. Before we had something along the z-axis and it was rotationally symmetric. So not a nice beam going out following an object or an airplane. But now here you can see that you have some array and you can see you have some beam propagating in some directions. And then by changing these coefficients to your array, you can really get it to scan almost everywhere. Of course, in these cases, when you see it here, especially this one here, you can see this one have an upside down symmetry, while the lower one only basically radiates upwards. And that you can fix by adding, for example, a ground plane under your array, or have, for example, a patch element. So if I take patches like that, the element patch pattern only radiates up, which means that I should multiply the array factor with the element pattern, and then I remove the beam that goes downwards. And then I have a very, very nice radiation pattern. And this is what you would like to have from an array. Narrow beam pointing out in any direction I would like to. That's a really good array. To do that, yes, you typically need 2 dimensions. Because to 2 dimension, you can control it like both this and like this. And you can get a nice beam. A 1D array, you can only control in 1 dimension. And it's usually not sufficient. For many applications, it's not sufficient. So that is what we can do with the 2D array. So we will not do a lot of 2D arrays here, because as you noticed, the thing we do with 2D arrays is actually 2 times a 1D array. So we just do what we did before, and we do it 2 times, and then we have a 2D array. Now we will come to a concept that we have skipped. So when we actually have been doing our arrays before, we really say there was no mutual coupling, which means that you had your 2 elements, for example, 2 dipoles sitting next to each other, and we say they don't talk to each other. They are like radiating like this one is radiating like this one. They don't care that they have a neighbor. In reality, they do care. And that is something called mutual coupling. We will not really analyze it, but we should know why it happens, and we should have an idea what to do with it. And then afterwards, we will go to what's called broadband arrays. And that is that you have a large bandwidth. And of course, when you have a large bandwidth, you cannot be at lambda/2 spacing. Typically, you have to be much closer. And that means you have an enormous mutual coupling. And then we will see that we, instead of saying that mutual coupling is bad, we will say mutual coupling is good, and we'll live on it in some ways. That's what we will do with the rest of these arrays. So the assumptions that we've been doing in these array factors has been that we assume something here. So we assume that the current densities on these antenna elements are proportional to their excitation coefficient, which means that if you have 0 excitation coefficient, there is no current on that element, which means that if I drive this element, I put this next to it, there shouldn't be any induced currents on it. In reality, there will be induced currents on it, and that is this mutual coupling. We also made an assumption that these current distributions on the elements are identical. So the shape are the same. That's also an assumption that we have been doing. And by doing that, we gained a lot, because we got these things, the principle here of pattern multiplication. So we got the principle of saying that we do the array analysis, we fix the array factor, we do the element patterns, and 2 different people can do them, and then we multiply the result together, and we have the radiation pattern. And it's based on these principles. And of course, in many cases, these principles are not correct. And then we need to be able to adjust for these things. So in real arrays, the interactions, the elements here, they do interact. So the current density on an antenna element, so the current here on this dipole, it depends on the excitation of this one, but also on the current on the neighboring elements. So if I drive a neighboring elements, they will spill over currents to the other element. And that's neglected in this analysis we've been doing. And the next thing is that actually the current distributions are not identical. So we made 2 assumptions. And now I say here that in real arrays, these are actually wrong. Does that mean that it was meaningless, that what we were doing? Absolutely not. It's still the dominant factor for most of the analysis. Most of the understanding sits in what we were doing. But in many cases, we need to take care of the other parts. So we need how to do it. And we can see it in many cases as a perturbation of what we did before. So it is the most important part. So look at an example here. So these are now a dipole antenna with some length here around lambda/2. And that is the driven element. So I should change maybe the color. So this lambda/2 is a driven element. All of them are lambda/2. And the element here is a driven element. So the one that sits in the center is a driven element with lambda/2. And then I take 2 more elements. So I take 1 element and I put it here. And in the first case, it has length lambda/2. And in the next case down here, it has half of that one. So that is the factor that we can see here, lambda/2, and this is 0.25 and 0.5. And I do the same thing with an element that sits a little bit further away, this element here. So it also changed the length, but most of all, I double the distance between them. So the red element, or with the currents, is much closer than the blue one. And then we can see what conclusions can we draw. What the conclusion we can draw is that when the elements have the same length, they are resonant at this frequency, they also induce quite a lot of current. So if I have an array here, I drive this element, I put another dipole element next to it, half a wavelength away, I will actually induce a lot of currents on this element, which is this mutual coupling. These plots are generated here with one of the codes in Orphanidis. You can run it yourself, you can see what's happening. And we will actually utilize this on the next lecture, where we will actually look at Yagi-Uda antenna. This is a basic principle of Yagi-Uda antenna, because what you can see here is that you feed this element, typically in the center, then you induce currents there, you induce currents there, which means you have an array. So by feeding one of them, you can get an array. And you just have to tune the phase of those ones to get a nice radiation. That is Yagi-Uda antenna, the old classical TV antenna. So this is this one. So this is actually how this one works. You can see a radiation pattern here when these are tuned. A nice radiation pattern away from a dipole element. So there it works like an array. And that is the case where this mutual coupling is really utilized. So a Yagi-Uda antenna lives on mutual coupling. You feed one element, behind the element you put something you call a reflector, sometimes a double element, sometimes a single element. It's typically longer than the driven element. In front of it you put directors, those are typically shorter elements, and then you choose the length and the separation to actually form what's called an end fire array. So it radiates in the direction of the array. And we will talk about this on the next lecture. This is a Yagi-Uda antenna that lives on this mutual coupling. Now we will see what effect the mutual coupling has. So it comes from different cases. It can come from the free space coupling. So this is the one I talked about. Two elements, electromagnetic waves interact between them. It can come from scattering of nearby objects. They can reflect in the ground plane or another object and then talk to each other. There can also be interaction through the feed network. So basically it could be anything. A lot of things can create this mutual coupling. What does it affect? It affects the impedance. It affects the radiation pattern. So maybe I should ask the question, what doesn't it affect? Virtually nothing, because if you think about your antenna, which are the things that we've been looking at? We're looking at the impedance, very important parameter, radiation pattern, very important patterns or parameter. Those are the important parameters, and they're all affected by mutual coupling. So mutual coupling really affects almost everything we have in these arrays. And then we can ask how fun it is. If you look at the impedance you had before a connection between a voltage and a current, and then we have an impedance. So the voltage is the impedance times the current. Now, if you have many antenna elements, you have many voltages, you have many currents, which means that you have a huge matrix here. And when we go to mutual coupling, this is what we need to do. So when we really talk about mutual coupling, we have this array perspective, and elements are talking to each other. And we need an impedance matrix. And now you can see one of the challenges of this is that, of course, to understand the impedance matrix of a dipole antenna, you can do, we have learned it in the course, it's not trivial. To do it with mutual impedance, it's virtually impossible. We need to go to computer software to do this, but we need to understand what sits behind it. And there we can get out this impedance matrix for the array in some cases. So we can do the same with the matching. So we can define the reflection coefficient. We will very soon take a break. And it does, in some ways, change things like incident signals, reflected signals, and it's not a localized thing anymore, it's big matrix. And it will depend on the excitation you send, the pattern synthesis, and the scan angle. So even the matching in these cases start depending on what signals you send. It doesn't do that for a single element, but it will do it for an array in these cases. And there are methods to analyze this. So that is also something that is good to in some ways know in these cases. Yes, we can do this. But of course, we will not do it in this course. We see that as a more advanced topic. So you should know about it, but it's not something we really utilize in this course. So we don't live on it in this course. We will just mainly say that they are there. And we will look at one specific case, which is called broadband arrays, where actually mutual coupling is everything. But that we will do after the break. So we will stop there. I will stop the recording of this.